You may indeed. All right, so we survived the quiz. Subnetting is what it is. We'll look at it again soon. Before we dodge into the last of Chapter 5 from last week and take a quick peek at what's coming up in Chapter 7 and Chapter 8, I wanted to look briefly at the project. Now, I'm hoping to have a draft of your project in hand, hoping to have it in hand tonight. Yeah, I thought that might evoke some laughter, because I have a train ride tomorrow and I would like to mark them or at least get an idea of where you stand as soon as possible. Specifically what I'm looking for. We're only looking at stage 1 of the project. Stage 1 is about the physical requirements for the network. So we're looking at the fact that you've read enough of the scenario to know, and the scenario, I've got it pulled up on the screen here, that you know how many computers there are in each room. So there are 6 different classrooms, classrooms 1, 2, and 4 on the first floor, 1, 2, and 5 on the second floor. Each one of these has got 25 computers in it. So in one particular classroom, I'll expect you to understand that there are 25 machines. 23 are student machines, 1 instructor machine, 1 server, it says. All right? So I want you to choose your student machines. You can pick something default from Amazon. That's perfectly fine. List the basic system unit. List the network speed that the port provides and what kind of a network card it is. In other words, I'm expecting to see what kind of a plug goes into it and what kind of a cable comes out of it when I say what kind of a network card it is, all right? So, RJ45, category whatever, yeah. So, I expect you to know that there are 25 machines in here, 23 student machines. You'll give me a system unit. You'll tell me the network speed it supports, what kind of a jack goes in, what kind of a cable's coming out. Then, within this room, one expects you'll have to hook all those things into something. I'd like the name of that particular piece of equipment, how many ports it has on it, what network speed it supports. Then, they're specifying an instructor machine. I don't see a reason for that to be significantly different from your student machine, but if it amuses you to pick something else, go for it. And they mentioned a server. As of yet, I need just basic server information. Later, you will have to tell me not just the system unit, but what services the server is providing. Now, I don't think each classroom needs its own DNS server as a personal opinion, all right? I'm assuming that a DNS server can handle the various scopes, the various subnets that you've got. So, pick out the equipment, pick out the network cards, the speeds, give me a couple of operating systems just so I know what you're looking at. Give me the things they all connect to, and then that means that you should be taking into account cable length. The building is 240 feet long. It's 96, I think they said, 96 feet tall. So if your router's on the ground floor and you're running something from one corner of the classroom over, down, and down, keep in mind the maximum length cable run that you can have for the particular type of cable that you're using. Until you need a repeater, until you need something, yeah. A repeater or, you know, a router will pick it up and rebroadcast, so. So there you go. One cable length, that's the maximum cable length, and so on and so forth. Physically, I think that that's pretty much what you're looking at here, yeah. The fact that you know how many machines are in each room, what cables, what network speeds and so on are supported, how you're running cables from one floor to another, what's being put together, more or less, okay? So I was hoping to get that kind of information soon. Now, stage 1 also asks you to choose services. Again, keep in mind that they talk about using private IP addresses on the wireless access point. They give you the network numbering scheme and tell you more or less where your subnets are, so you have to work that out as well for the next stage. But the network services, you're probably going to need some things like that you've been studying, DHCP, DNS. We're going to talk about firewalls tonight, and you're going to look through the modules for it this weekend, so I'm assuming you'll have to pick out a firewall, and so on and so forth. Questions about anything to do with Project 1? The sooner I have it in hand, the sooner I can provide you with some feedback, the sooner you can then revise it, and we can go through the loops until everybody's comfortable. I know that we haven't been in class. It doesn't feel like we've been in class that long. I'm sure it feels like forever to you. But there's 1 month left, literally, from today. So in 1 month, we've got the rest of this to get through, and 2 more stages of the project to do as well. Subnetting, you're going to have it'll be super easy after what you did tonight for the quiz. So that part of it you should be able to dash that off, and that's easy. That's good stuff. All right, that's the project more or less. Remember, that's where the descriptions are. You've seen the template. Life is good. All right. Brings me back out to here. We finished up looking at subnetting last week, and there's a really long, boring lecture on it. My own boring lecture, plus a couple of other boring lectures posted in the classroom. We didn't get as far as the last couple of super easy topics from Module 5. DHCP and APIPA and domain name resolution. So I'd like you to just envision this laptop that I'm working on. It woke up and asked for how does that work? It didn't have an IP address when I turned it on. I put a network cable into the back of it. What happens? DHCP, Dynamic Host Control Protocol. What does that mean and what does it do? Absolutely. So it can, certainly it's going to give out an IP address. Specifically, my machine shouts on a particular broadcast address. Excuse me, I need an IP address. So that's broadcast out. And if all goes well, it's picked up by a router, and then it depends. If the router is RFC 1542, I had to look it up. If it's a compliant router, then you can enable it to forward a broadcast onto a DHCP server. By default, routers drop broadcast packets, okay? So any broadcast message that hits a router is discarded. It doesn't bother routing it. There's a specific IP helper setting that you can configure that recognizes a DHCP request, and then it has the IP address of the DHCP server stored in the router. It forwards it, instead of as a broadcast, it forwards it as a unicast packet directly to the DHCP server. So, as long as you've got a DHCP compliant router, it'll forward it directly to that DHCP server. If you don't have a DHCP compliant router, then you have to have a server on the subnet. And that server has to be configured under the remote routing and access services with a DHCP helper function. And what it does is the server listens for DHCP broadcast requests. And if it finds one, it then readdresses the packet to a DHCP server, and that way when it hits the router, it gets to the correct address. So client shouts, hey, I need an IP address. The IP helper on the router or the server says, okay, let me forward that to the IP address for a DHCP server if it's on a different subnet. The server says, okay, I hear you. How about this IP address? Do you want this one? And the client then accepts the request, acknowledges that request, and the server acknowledges the client's acceptance. That's the 4-step process required to get a DHCP address. Now, when it hands out that IP address, it also can give the default gateway and the address of a DNS server. Those are things you set up on your DHCP server as part of what it can hand out when it hands out IP addresses. Questions about DHCP generically?
So if you have a DHCP that's already set, so that way you can hand you out some DNS, an IP.
Yep.
You don't need a DNS server.
I still need a DNS server because the DNS server instead looks at the domain name
Right.
and keeps a table of domain names and matching IP addresses. So DHCP simply says, oh, you've got an address like www.aardvarks.com. I don't have an IP address for that. The DNS server has that. The DNS server provides that lookup for you. It's a phone book, the giant phone book of the internet, DNS.
Right. Based on how we conceive the numbers, because we can't.
Because we're not happy with
IP
binary.
addresses.
Yeah,
We
in
can't-
general. Yep.
We can't do IP.
So they're two separate services, and they're both very, very important. And there are huge security concerns if you're managing a DNS server. You may hear about SQL, structured query language injection attacks. And what that does is it looks at one of these big phone books, a DNS server, and it says, well, you've got a record in there for Amazon.com, and you think the address is 205 dot something, but in fact, I'm here to tell you that we've updated our address, and Amazon.com is really at this address now. And if you can fool a DNS server into writing that down, then the next time somebody goes to Amazon.com, it will give them the bogus IP address, which can be a spoofed server that's stealing their information. So it's common, yeah, for those kinds of attacks to take place. So people look for domain name servers who haven't been patched, who haven't had the latest updates, who somebody's not really keeping an eye on, and then they sneak in and try and rewrite the phone book addresses so that you get the wrong server response.
So the DNS server and the DHCP are constantly talking. Because, or is,
They don't have to. You can decide in advance. Your DHCP server, he's just the guy that's responsible for handing out the ticket numbers. Go here, go there. Instead, the DNS server, he's the one that's constantly updating the phone book.
but where, because you're attaching a domain name to an IP address.
Yep.
And a DNS.
But most of those great big
Who are giving it to them?
most of those great big companies like Amazon.com, you're not going to get them asking for a new IP address every time they wake up.
Right.
So they're going to have kind of a permanent, either a static one, it's pretty static. And as they update, then they update their big phone book. They'll have a server which is responsible for Amazon.com. It's called the authoritative server for the zone. So Amazon's got its own little zone thing going on. And when they change one of their server addresses, it changes their phone book, and their phone book then pushes that out to other DNS servers.
And it's all based on the IP address, right?
It's all based on the IP address. Yes,
So
sir.
it says, all right. Okay, all right, I don't want to get too.
That's all right. We're going to get to it again in just a second. So you know how an IP address is received, generically DHCP. When do you use static IPs? You use them for resources that you don't want to change frequently. Printers, servers, your gateway, your routers, those kinds of things maintain a steady route so that these guys, when they wake up, can find the resources that they need without having to constantly go and reconfigure themselves. So some things on a network will be statically assigned, some things on a network, or most things on a network will be dynamic. That's a happy thing. If my machine wakes up and it cannot find a DHCP server, now there are lots of different reasons for this. It may be that my switch is bad, and so it can't get to the rest of the network. That it may be that the DNS server, or that the DHCP server itself is down for whatever reason. It may be that the router is not forwarding DHCP requests. It assigns itself its own personal IP address. Those APIPA, Automatic Private Internet Protocol Addressing, you don't care what it stands for. The APIPA addresses start with 169.254. When you look at an ipconfig/all and you see a 169, it means your machine is not getting an IP address from the DHCP server. You can try release and renew. If that doesn't get it for you, you need to start pinging to see where you can go. Are the machines around it having problems? Are there problems at the switch, problems at the router, and so on and so forth. All right. So APIPA, there we are. Then, DNS name resolution. So here's the deal. This machine is looking for aardvarks.com. Aardvarks.com, is it something I've used recently? It'll bring up in the local disk C, traditionally, Windows directory, System32 directory, the Etsy folder. Yeah, you don't care. You used to have to, and it's not even displaying here, is it?
Yeah, we got to go ahead and see, right?
It should be ETC, shouldn't it?
I think it was up a little.
Drivers, it's in drivers and then Etsy. So let me go up one to drivers. Inside of drivers, inside of the area, there it is, Etsy, all right? Hosts files, all right? So it wakes up looking for aardvark.com. First thing it does is it looks, let me open it up using Word, looks inside of a local file to see, do I already have an IP address and a domain name on file locally? Is it something I've used locally? Then, if it cannot find it on the local host, the next thing it does is it looks for the DNS server for your local zone. So, aviano.af.mil, a lot of the folks on the aviano.af.mil network are going to be reaching for resources that are also part of aviano.af.mil. Some of them are looking for stuff on the internet, but a lot of it's an internal stuff. So you will have a DNS server for the aviano.af.mil network that stores commonly used resources, commonly accessed web pages. It goes to what is known as the authoritative server for your local zone. UMUC.edu locally here, our lab, we don't have an authoritative server. It's not like this is a huge company with lots of different resources that are available. Instead, our internet service provider gave us the name of a DNS server that is local, responsible for local zones. So they provided us with that DNS server. So not on my local host file, it's going to go out, ask the DNS server that was provided by my ISP. If it's not available there, it goes not to the next level up, it goes all the way to the top level. Now, domain names are resolved from the dot, literally the name of the root server is dot, period, D-O-T, dot. So it goes there first, and it says, she's looking for aardvarks.com. Root says, my commercial zone is over here with .com. Let me hand you to the .com top domain level. If instead I'd been looking for aardvarks.gov, it would have handed me to the .gov top domain level. So you go down one branch to the top domain level. From there, .com says aardvarks, aardvarks, aardvarks. Wait, my aardvark company is over here. Let me hand you to their authoritative server for aardvark.com. And at that level, somebody says, oh, the www server, that's located at 174.530. You get the idea. They give the IP address for it, and then that's passed back to my machine. From then on out, both my local domain name server has a record for it, my local host file has a record for it. Folks, write down that, because if I'm requesting it once, there's a high probability that I'll request it again. Much easier to resolve it closer to home the next time. So, check it locally, check the local DNS, the authoritative server, go to the root to top domain level 2, company kind of level. Whatever that server is, it's responsible for all the services within its zone. For example, I've got www.europe.umUC.edu. If you were looking for this web page and it weren't cached locally, it would go to the .dot server, which would hand it to all educational servers. Within educational servers, it would hand it to UMUC. UMUC has a domain name service server that is responsible for keeping track of which machines belong to the European zone, which machines within the European zone belong to the faculty.umUC.edu, which ones belong to mail, which ones belong to admin, and which particular server. This is a specific machine named www. It's tradition to name it www. It is the address of a particular machine, or of a group of machines that all resolve to one IP address that's then balanced out. So top level domain edu, within that authoritative domain UMUC, within that Assuming that UMUC were some multi-IBM-sized, Amazon-sized thing, you might have subdomains, one for Europe, one for Asia, one for the US. But here I think we can resolve that UMUC is the top-level domain for our particular organization. Questions about domain name resolution? Okay. Too easy. You asked earlier, are the DHCP server and the DNS servers in constant communication? And I said, well, technically they don't have to be, because DHCP is just responsible for handing out IP addresses and telling people where to go to look stuff up, where the phone book is. But in an organization where IP addresses are assigned to machines that may also hold resources, the DNS server is, in fact, you can dynamically update the DNS server by asking the DHCP server to notify the DNS server when it assigns an IP address to a resource. Was that English?
Just run it by me one more time.
Let me do it again. Here we go. You've got your DHCP server. All he's responsible for is giving out IP addresses.
Take that.
And he's pretty good at saying, and the phone book, he's over there. And he doesn't have to do anything else. But in an organization where some of those IP addresses may be given to a machine that holds resources for somebody else. So you might have a shared drive, or you might have a printer that's actually physically attached to somebody's machine. These kinds of resources that somebody else may need to access, and that resource may even have a name, then it's possible, and in fact quite likely, that your DNS server can be dynamically updated by your DHCP server. So this machine, which is attached to a printer, wakes up, says, hey, I'm your printer guy over here. I need an IP address today. He says, okay, your IP address is this. Then he goes back out to the DNS server and he says, oh, and by the way, if anybody's looking for that printer, this is where it is. So you can dynamically update your DNS server as well. Then, inside of your DNS server, there are different types of records. An A record takes a domain name, resolves it to an IP address. That's what we think of when we think of DNS. A quadruple A, AAAA, quad A address is an IP version 6 record for a domain name. A is IP4, AAAA is IP6, MX is a mail server, CNAME, canonical name, is an alias, and a PTR record is a backwards name resolution. When you say, oh, 192.168.0.103, who is that again? And it says, oh, that's www.aardvarks.com. So you can do it backwards. It's like a reverse lookup in a phone book as well. Those are aliases. So for example, I might go to my mail server, but in fact, my mail server is probably really about 30 different mail servers or 5 different mail servers or whatever it is. And rather than say, you know, mail.umc.edu is at this one IP address, I might have one IP address responding for mail, and then I might have 5 or 6 other CNAMEs. And what it'll do is it can choose any of those. If the first one doesn't respond, it can go to the next one.
Right, that's why sometimes you can just, you don't have to put the whole name. You can just put a particular name in there and just click enter.
And it fills it out. And in fact, your DNS server contains something called root hints. And the root hints tell it what suffix to put onto a domain name to try first. So for example, if you're working for umc.edu, and we're all in-house in the company here, and I'm looking for mail, and I type mail, rather than go to mail.com, which is a traditional thing, it'll automatically, based on the root hints file, append .umc.edu, for example. So.
And it attaches it to it.
And fills it out automatically.
That's what we do.
So those DNS servers, you've got one for each zone that you are an authority over. And you have 2 different types of DNS servers. You have a primary server and a secondary server. The primary server is the real authority for the zone. Therefore, if I change the IP address by adding a server, by removing a server, by doing something to a server. It's going to update my primary zone server, and then that information is pushed out and it replicates to other DNS servers across the world gradually.
So is this what we're talking about with Amazon.com?
Amazon.com. This is part of what we're talking about with Amazon.com, is that when they update their Amazon.com server to say, okay, now if you're looking for this kind of a thing, it's on this particular server, it updates Amazon.com. That then pushes up to the .com top domain level, which then pushes up to the root level, and it trickles out to wherever else it needs to go so that folks can resolve it successfully. A secondary zone server just contains a copy of the DNS information so that it can then provide that information, but you can't edit a secondary server.
So
Mhm.
that's the guys that Amazon sends all the information to.
Mm-hmm.
So that way, anybody looking for Amazon
Yep.
gets the information from that DNS server.
Yes. So Amazon.com will have, Amazon.com has its own set of DNS servers.
Right.
So you can hit half a dozen of them. Some of those are editable. Most of them are not. Most of them are copies that make it easy for people to look stuff up. It's kind of the way that, if you don't remember what a real phone book looks like a paper-based phone book, you can look it up on Wikipedia, okay? It's kind of the way that I can cross off a phone number in the phone book if I know that it's updated, and I can change it. But my changing my local copy doesn't do anybody any good. Instead, if a company has literally changed their phone number, they need to make the edit at the actual phone company so that the next time the phone books are pushed out, everybody's got the updated address. So it's kind of that level of a change. All right. The next part of Chapter 5 talks about IP version 4 versus IP version 6. Most of us are still using IPv4. Problem with IPv4 is that it's only 32 bits, which means, you know, it's got those 4 octets, which means you can only cover something like 4 billion devices. That doesn't sound like we would run out anytime soon, but when you consider that toothbrushes and refrigerators are getting their own IP addresses these days, and that most of us are sitting here with, you know, a device in our pockets and another one, you know, a tablet and a laptop and all this other stuff, phones and everything else, and that some of them have multiple network interface cards, 4 billion addresses isn't getting us nearly to where we need to be for the Internet of Things specifically. So they've expanded it. IP version 6 has 128 bits. We have to write it out in hexadecimal because it's so bulky. So there are 8 different slots. Each slot has 4 hexadecimal characters. They're bulky and awkward to look at. So this is an example of an IP version 4 address. You notice that it's supposed to have 8 slots, but I've got here 1 slot, 2 slots, 3 slots, 4 slots, 5 slots. Where are the others? The double colons, there are 3 sets of zeros in between. So IP version 6 is available. Most of us have not yet switched to it. Some places have, however, and IP version 6 uses slightly different protocols, obviously because it requires more bits for just the network address. So if you've got 2 IP version 6 hosts and they're trying to talk to each other, and the intermediary network is running IP version 4, the routers are IP version 4 routers, which a lot of things are, then you need to fake it. So they've got these tunneling protocols. One's called 6/4, 6-4. One's called ISOTAP. One's called Teredo. These are using network address translation, which we're going to look at again in just a few minutes. But the reason that they're likely to pop up, you just need to know that they allow IP version 6 to function over IP version 4. The reason they're likely to pop up, here I've got my command line interface pulled up. I had it pulled up and then I got excited and pushed it out of the way. All right, and let me clear the screen really quickly. Let's go to ipconfig/all, and you're comfortable and familiar with all this stuff, or at least a lot of it. Up here, they've misnamed my laptop Live Streaming. Never mind. Down below, DNX suffix search list. This is my root hints file, homenet.telecomitalia.it, because the DNS server that's providing my stuff assumes that I probably belong to Telecom Italia. I'm part of their company. That's who my ISP is. If I'm searching for a source and I don't add on a suffix, it might append that to it. Down below, my local area connection Ethernet card has a physical address. You're comfortable with the media access card address being hexadecimal. First 6 characters are the manufacturer, the last 6 characters of the card, you don't care. DHCP is enabled. Yay! Yes, it is. I don't have to hard code a static address in. Then it gives the standard IP version 4 address, and there is the IP version 6 address. You can ignore the %14. It's huge. A lot of addresses. Then the subnet mask. This is a Class C address. We've got the standard classful 255.255.255.0. My lease was picked up then. It expires then. Halfway in between, it asks to renew it if I need to. All right. And then down below, the default gateway. That's given out by DHCP. The DNS server, given out by DHCP. And then, as I scroll down, some of the stuff that we don't normally look at. There's an ISATAP. This thing is capable of using IP version 6 and faking IP version 4 if it needs to talk to an IP6 device. Down below,
I kind of skip over all this stuff.
I don't blame you. I would skip over, but look here, here's Teredo. It's just another, it's not a real network adapter. There's no physical adapter in there. This is a piece of software that is going to mimic being a network adapter that is capable of working with an 128-bit address. That's IP version 6 as far as this particular section of the textbook is concerned with. You've seen the words ISATAP and Teredo. We're going to get back to network address translation in just a minute. Something else from chapter 5 that I thought was interesting. Multicast. So, I don't know that if you've taken a live streaming class. If you haven't, they're an interesting opportunity for you. I highly encourage you to look into those, all right? Because if you cannot scare up enough bodies to get the class that you're looking for face-to-face, you know you need technically 12. I'll normally slide it in with 9 because they figure 3 guys are going to drop anyway. But if you've got 3 or 4 folks that need a particular class and it's being offered at a location which has decent bandwidth, they have the ability of setting up a webcam, setting up a microphone. You dial in, basically, the specific program that we use to dial in is this VC program, really low maintenance, designed for the Department of Defense, all right? And that VC opens up something that looks an awful lot like Skype. I can see you, because there's a camera in the classroom pointed at you. You can see me, because there's a camera in the classroom pointed at me, or when it's in my classroom, it's not pointed at me, it's the whiteboard, that's what you get. And it's live. I lecture, you can ask questions as it goes. And so a class running at another location can have 12 students locally, 5 students in Aviano. It counts as just a regular hybrid class. You all get together in one room once a week and you can live stream the information. So how does that work? Well, the packets of information that I'm sending are not sent 6 times for the 6 different students. Instead, it's sent once. Because when you register, when you connect your live streaming client to the session, it gives you, in addition to your standard IP, it gives you a multicast group address. So it's got a little group and it says the following 6 guys belong to this group. And the routers between you and me make note that that group address also needs to be sent to whichever arm of the network you're on. So it sends out one video packet to the local router. Local router picks it up, and it's to the multicast address. Local router picks it up and says, okay, this packet needs to go here, and it then sends it to those folks. If they're all on the same network arm, it's still one packet. Otherwise, if they're on different network arms, it goes to different places. Yeah. So it cuts down on traffic by, instead of us maintaining 6 separate sessions, I've got one session going, and the packet is addressed to a group of 6 people and delivered to those 6 people individually. Sir,
This is group D, right?
this, the multicast addresses come from D, from a class D network. Yes, they do. So that's what multicast does. The router has to be IGMP. Now that's the protocol. We looked at ICMP, which contains ping and traceroute. IGMP is the group version of that. It's a multicast kind of capability. So the router has to be able to handle the IGMP Internet Group Management Protocol. There we go. And it forwards it to the routers, and then those deliver to the individual group members. So that's what multicast is and how it works, in a nutshell, the Cliff Notes version. Then, cool thing about Chapter 5, they gave you a whole lot of tools to look at. ipconfig, ipconfig/A, which you've used enough now that we don't need to go over it. ipconfig/release, lets go of an IP address. ipconfig/renew, requests a new one from the DHCP server. Then, ping, you've used nonstop. Ping sends out a message, and you expect the resource to reply with its IP address. Traceroute, you've used nonstop. It sends out a packet and decrements the time to live so that each individual device between you and the destination device replies with a message saying it made it this far. Got it. ARP, netstat, nbtstat, nslookup, and dig. Dig is a Linux tool. So we were looking at a few of these. ARP, I use ping instead of ARP. ARP, all it does is it looks in the routing table and resolves a name. It gives you an A record. So I put in aardvark.com, and it responds back with the IP address of aardvark.com. So can I do that from here? Let's try that. I've got ARP-A, and then I should be able to put in, can I do that? Bad argument. It doesn't like google.com. Let me see what I'm doing wrong here. Oh, this is just giving me all of the things that I've got in my local table.
Are you talking about like a DNS server, Sarah, or your actual?
This is my local hosts table that's telling me what address resolution records I already have on file.
Wait a minute, for your host.
Yep.
For your host. So these are all.
Things that I have reached for, or things that have been recorded statically in my local machine.
Like printers?
Well, not necessarily printers, but maybe printers. So what can you see that we recognize so far?
The 168.
Well, I can see down here on the, because you're only interested in the 192.168.0.103 interface. The other one's not real, all right? It's a bogus one that's used for tunneling. Instead, 192.168.0.1, that's the MAC address that it belongs to. That was given to me by my DHCP server. Instead, 224.0.0.2 has been statically assigned. Somebody has coded that in as something that's important. 255, 255, 255, 255, that's the broadcast address. And it's statically assigned. So some of these other things, they've told it that I need to remember where they are. And some of them are being passed out by the DHCP server. So the ARP protocol, and I don't even have my notes open. I should have my notes open so I can read you all the interesting things that I thought of when I did this. ARP is one of the things that we've looked at. You've got labs that use ARP. There we go. And in fact, if I do ARP and I do a question mark, does it give me, there they go. These are all the different switches you can use with it.
R-S, R-V.
Yep. So anytime you need that, you can just put in ARP dash question mark, and then it tells you this will display the IP to physical address resolution tables used by ARP for you. Okay, so we know a little bit about ARP. You've seen it more than once now. NetStat. NetStat, instead, if I type NetStat and a question mark, it gives me all of the switches for NetStat. And NetStat here tells you what current TCP/IP network connections you've got. So if I do NetStat, and I think it's -O, maybe?
That's displayed the only process ID associated with each connection.
Oh, I have no active connections. No, I should have it. No, there they go. Okay. So currently, my machine is using TCP/IP to go to 199.27.105.107, and that's process ID number 1896. What does that mean? That means that if I do Control-Alt-Delete and I bring up the task manager and I look for process ID number, we said it was 1896 or something like that. Where is my process?
You did it, your processes.
I don't see the ID numbers. Maybe I have to add a column. I want to see, can I expand it?
And you can stretch it out, you can stress it out.
Yeah, but where's the process ID? I should be able to add a column here. Maybe it's because I'm not in here as me. Here's process IDs for some of them. Let me do this. 18, we said, 96. I don't even see it here, but it'll be under processes. If I could add the process ID here, you would see it.
You have a whole bunch, you can scroll down and you go over there.
Yeah, but I still can't see the process ID number. So there is a place to go in here and open it up and see what the process ID number is. I used to be able to just right-click and add the information here, but I'm just not seeing it. We'll have to look up how to do that. But it would correspond to whatever it is I'm doing out here. I'm guessing that 199 is potentially one of these servers out here. Yeah? Instead, it tells me that I've also got going on here, some of it's going to server-54-192-185. That's HTTP. That's a web page. Some of these others are web pages. And I can see that's going from me to another address. So that's what NetStat does. It tells you what current, basically, ports are being listened at.
It also tells you if you're doing live streaming as well.
And whatever else is going on out there. Yeah. All right. Okay, so that's NetStat. NBTstat. NBTstat, I thought you would find the most confusing because NBTstat is used for NetBIOS names. Did I just put it in and get it wrong? NetBIOS names. So we've been working with TCP/IP and working with IP addresses and host names, which are the ones that are used in the great big wide world. Instead, each machine, Windows likes to give it its own little name, and you belong to your own little work group. And those own little names that you're using are NetBIOS kinds of names, basic input-output service names that can be used on a network without using IP addresses and all the grand good stuff that gets you out into the real world. So NBTstat is a way of looking at NetBIOS over TCP/IP. It's mentioned very, very briefly. It's mentioned as a tool. It's not one that I think you're going to have a lot of time for, a lot of need for. NSLOOKUP is the one that I use ping instead of. All right. Enough about the tools for now. Instead, this week you're going to be covering chapters 7 and 8. 7 is on routing and 8 is on firewalls. 8 is luckily fun and easy, not a difficult thing at all. 7, on the other hand, is not the most beautiful thing I've ever seen in my life. So here's the deal. A router, as you know, chooses the best path for the data to take to get to the destination. It's choosing the next step on its way. So how does a router do that? Well, it depends on what kind of a metric it's using to decide what the best path is. So, these metrics include things like how many different hops are there between you and your destination, and I'll choose the route that has the fewest hops. That sounds like a logical way to do it, right? Instead, a different way of looking at it is which kind of connectivity do I have between routers? I'll choose the one with the fastest connectivity. So you might have one path that only has to pass through one router, but it's on a 10 megabit per second connection. And instead, this other one over here has to pass through two routers, but it's on a 100 megabit per second connection. It's faster to take the 100 megabit per second connection even if it has to go through two routers. So depending on what kind of protocol is installed, it will choose to use hop count as a metric, bandwidth as a metric, or something that the administrator has to set, which is called link cost. Link cost can be used to determine if one path costs more money financially, or costs more money politically, or costs more money security-wise. So an administrator can choose to choose one of these different types of protocols. So the types of protocols that you're looking at, they hit RIP, which counts hops to determine which is the most effective route. They talk about EIGRP, which looks at bandwidth to determine which is the most effective route. And they look at OSPF, Open Shortest Path First, and IS-IS. Both of those, the administrator sets the cost for those. So this is the type of protocol which is enabled on your router that determines how your router decides what the best next step is. Once you've determined what protocol is being used on the network, your router itself will keep a routing table. It looks very much like the ARP table that we looked at earlier. So, the routing table tells you the destination. Now that's either a particular host or it's a network that you're reaching for. It gives you the network mask to determine whether that's something local or whether it's going someplace else. And then it tells you the gateway to get to that particular step. And the metrics here, they're all ones. If you were using RIP, that would mean that they're all one hop away. Instead, if you were using OSPF, it might determine that that's a good choice as opposed to something that politically or financially costs 2 or higher. I've stopped. I can hear myself, and it's awful. So sorry for the people who are listening to the recording later. Luckily, this should put the baby right to sleep. So we've got the router there. Life is good. We understand routing tables generically. Well, how does a router determine, a router that's connected directly to my network and 4 other subnets, it knows where those subnets are. All of those have a metric of 0. There are no other routers to pass through to get to that arm of the network. Instead, how does it determine something like Amazon.com, the best way to get there? Well, it's counting on one of 2 different types of sharing principles, all right? One is called link state, and the other is called distance vector. So you've got router A, router B, router C, router D. With distance vector, each router knows the routes that are directly attached to it, and they send that information to their neighbors as well. Their neighbors update. There's a beautiful graphic inside of the actual lab, but did I copy it out? No. The neighbors update their routing tables with the information router A sends, and then they send their routing table, which is their direct connections, and the routing information that A sent to them, they pass all of that along to their next neighbors. So distance vector shares all information and just keeps pushing it out, and each router updates its information as it receives new information. Instead, link vector, router A sends its connections to router B. Router B then sends only its direct connections to router C. It doesn't bother sending router A's information on across. That's the link state direct routes only, link state. 2 different ways of deciding how much information a router shares with other routers. One, it updates everything. including information that it doesn't know firsthand, it's gotten it through the grapevine, and the other, it only passes on information that it is confident of because it's its own personal link state that it's passing on. All right. It's important for you to know that you will determine on an interface by interface basis how much information is shared with neighbors. On your internal network, it's great. Share away. You want all of the routers on your internal network to know where all of the resources are so that they can quickly and easily route packets to the correct destination. But you do not want your external interface, the one that reaches out into the rest of the world, you don't want it sharing the internal routing tables with the rest of the world. That's private internal information. So your external router should not be set up to share routing information. Hang in there, folks. A little bit more. Chapter 7 also talks about VRRP and GLBP. And HSFP, I could be lying about the last one. All of these are procedures for having a backup to your default gateway. So, right now my default gateway 192.168.0.1. If that goes down, I don't have another route onto the internet from here. My router goes down, I have to call the company and they bring me a new one. But in a company, you're likely to have more than one way to get out to the rest of the world. So, if your default router goes down, everybody's offline until you can go in and either replace the default router or update the address of the default router to a different default router and then push that address out to everybody else. Make everybody drop their IP address and pick one up, and that'll get the new default gateway. Instead, happily ever after scenario is that instead of using the real IP address of a real router, you assign a virtual IP address, a virtual gateway, and then your DNS server uses canonical names, CNAME alias names, to point to several different possible default routers. Now, it may be that you're only going to use one and it's only if it fails that it rolls onto a backover. Or it may be that you're load balancing and that because one router tends to get pretty busy, you're directing some of the traffic to a different router to get out onto the rest of the highway. So that's what those two things are about. They're about having a backup gateway or a backup default route of any sort. It doesn't have to be a gateway, but a default route. Having more than one possible way to get to your final destination.
Almost like creating a mesh.
It's like the routers themselves are physically meshed, but you're giving this machine one default gateway. Or if it's got the router in the corner, if it knows the best way to get to the mail server and it's got that default route kind of coded in, then if the route that it's chosen goes down, it may need physically updated. Somebody might have to come and update a static route to tell it the best way to get to that other. This happens, for example, if you've got a company with a remote site and you've got a best path to get to the remote site without it asking its way each time. You can statically tell your router the fastest, best, lowest cost route to get to us is. Don't bother asking everybody else, this is the way to go. But if something goes down, even though they're physical connections, your router's going to keep trying to send it on the route that may have a block. So instead of assigning it a default real route, you can assign it a virtual next step and then load balance that so that it takes the best path of one of several.
Is that like the alternate?
It's like an alternate, yeah. Yep. Yes, and you'll do that in your routing table by having an IP address that doesn't belong to a physical device. And instead, that IP address will resolve into 2 or 3 other machines. So it can choose one of many to get to where it needs to go. The name for this is GLBP, Global Load Balancing Protocol, if I'm not mistaken. I'm probably lying to you. It'll come back up in your notes when you go through the stuff. And it has a virtual IP address, a virtual media access card address mapped to more than one, to a mesh of paths to get you to the destination that you desire.
Is that what the internet uses? Or are we just saying it's just like?
The internet
Internal.
the internet shares that information. The routers are all sharing with each other the best path for any given packet, and therefore a packet can take a variety of different ways. It's only when you're trying to get out originally, or when you've got a remote resource that you've got kind of a particular way you'd like it to go, that you need to do this load balancing or backup default. Because by default, the internet is a mesh network, and they're constantly, the routing tables, they're constantly updating each other. So they don't have to have a virtual load balancing protocol. They do that. Instead, in your in-house network, there are particular paths that you've got, maybe not a physical best path to, but a logical best path to get to keep it from bouncing all over the place and having to constantly update. That's what this is used for. It'll make more sense when you've seen it a second time, I promise. So if your routers are all updating each other, and two routers disagree on the best path to get to another device. So router B is in the middle, and router A says the best way to go is this way, and router C says the best way to go is this way. Who does it know how to trust? Well, it's got this little administrative distance calculation algebra that it does. And it says, if the router that is talking to me is directly connected to the other network, I trust him best. He's directly connected, the administrative distance is 0. Instead, if two routers talk to me and one of the guys hard-coded in a static route, I'm going to trust him before I trust somebody that's using a protocol that's getting its updates from somebody else. Because I'm assuming that the guy that sat down and coded it in knew what he was doing and that's the best path. Instead, if it's not hard-coded in and it's not directly connected, if the protocol you're using is OSPF, I trust it more than if the protocol you're using is RIP. That's in there. You've seen it once. I'm moving on. We're almost done. The end of chapter 7 also talks a little bit about network address translation. This is super cool and super easy. So I've got a private IP address here, 192.168.0.103. You know that I can't send a packet with that IP address out into the actual World Wide Web because lots and lots and lots of machines in the World Wide Web have 192. It's a private IP address. So instead, I will have a device. Sometimes it's a server. Sometimes it's a router with this service enabled on it. Sometimes it's a firewall, which can be a router, which can be a server. And this is the house. It's a device, and that device has a public IP address. That's the address that the rest of the world sees. And when I send my request for a web page out, 192.168.0.103 would like to look at www.aardvarks.com, which has an IP address of blah, blah, blah. I send it out. My network address translator device picks up the packet, opens it up, looks at it and says, okay, you want to send this out to the rest of the world. You can't do that with a private IP address. I will mask your IP address. I'm going to use my public IP address as the source IP address for this packet. And when it returns back to me, I will know to turn around and hand it to you, specifically client number 192.168.0.103, because I'm going to put a bogus port number on it, a virtual port number. Network address translation is also called port address translation. At heart, it puts a public IP address and an internal note-to-self port to know which client to return the traffic to on the inside. That's what it does. And in fact, if you look at your IP config and then you go to Google and you type in what is my IP address, the IP address for the public interface is different than the IP address of your private interface. When all of the rest of us, it's IF,
I still don't know how to get to it. I don't even know how to get to that screen.
terminal emulation, under terminal emulation. Yeah, it's there. You can you'll Google it, you'll find it eventually. But every machine in this room, if we all requested aardvarks.com at the same time, aardvarks.com would get 24 requests for that web page from the IP address 95.241.205.208. It would look like 25, like I requested the page 25 times. That page would come back, the server would pick it up and look to say, okay, when I sent this first request out, it came from client number 192.168.0.103. I gave that port number 103. Here you go, here's your web page. Oh, and you've requested it too, here you go, here's your web page. And it would keep track of the internal stuff on its own little network address translating table. That's the service that it runs. So that's NAT in a nutshell worth of NAT, right? That allows us to use these private addresses, the 10.0.0.0 through 10.255. Those are private addresses. The 172.16 to 172.31, and the 192.168, which is, most of us are familiar with that because that's what most of us use in an internal network. All right. A kind of offshoot of this is port forwarding. And that allows a resource that's out on the World Wide Web to reach for a server that's on your private IP. So my internal network might have a server in the corner, 192.168.0.237, and it's statically coded. I can't use that in the rest of the world. But if somebody needed to reach for a web page on my internal network, my network address translator would mask it and pass the packets into that World Wide Web server on my internal network, and then mask the packets going back out as well. Many people look at this as similar to a proxy server. So let's look just very, very briefly at the last topic of the day. Firewalls are in Chapter 8. Now, a firewall is very similar to network address translation. Many firewalls translate the addresses for you. And both of these are very, very similar to a proxy server. Here's the slight difference. Network address translation, all it does is it masks that private IP address with a public IP address. It's not looking at the packet contents, it doesn't care. That's all it's responsible for, is keeping track. Instead, and it acts at layer 3, which is where IP addresses live. A firewall also begins at layer 3. The simplest firewall uses an access control list, and it looks only at IP addresses to make certain that it's not a blocked IP address. Whitehouse.com gets a blocked IP address. Or it will look at the ports to make certain that this is an active session, it'll look at the port, not the session, it'll look at the port number to make certain that you're not trying to access port 21 when there's no FTP server internal to your network that should be giving information out on port 21. So most firewalls at layer 3, for example, allow port 80, which is web pages, but block port 16 through 23, or if you don't have an FTP server, 21 and 23 are blocked. So that's the simplest type of firewall. A layer 5 firewall looks at session IDs. Layer 5 is the session layer. And what it does is it tries to check that the data that's being sent in was requested by a machine inside the network, that there's an active session going on, that the session IDs are still open and listening and active on both ends, that the conversation was initiated from inside and is a continuing conversation. So it looks at the session ID at layer 5. The highest level acts at layers 6 and 7, specifically at layer 7. It uses an access control list to check for keywords as well as URLs. So it will make certain that certain uniform resource locations are blocked, and it will look for key terms. You know, gaming websites, YouTube can be blocked, or key terms on the page. It'll actually look at the data in the packet to determine what should be allowed through and what shouldn't be. So firewalls work at layers 3 all the way up to layer 7, examining the content of the frame and the packet as it goes back and forth across the network. Firewalls, by the way, can be hardware. For a company, you want a hardware firewall, a dedicated firewall. Instead, most of us are familiar with the firewall software that runs on an individual machine, and it's not as robust, not as strong. We'll get back to security much later, but this was Chapter 8 in a nutshell. And a proxy server, by the way, does something beyond network address translation, although it does offer NAT services. It can, although not necessarily will it, provide firewall services, but a proxy server attempts to handle the request for information literally for you. It acts in your stead. It acts as a proxy. So many of you are using proxy servers to get around, for example, video streaming restrictions. The proxy server not only may request those video packets from somebody else and then turn around and hand them to you, but in fact it may host some of those video streams on its own and pass them on to you. The rest of this chapter has a huge list on common ports. We don't need to go through them here. You can read about the common ports in the list that's in the textbook. It also mentions that for a home office or for a small business or for a business that doesn't have a very robust security, your firewall may be combined in one giant unified threat management device, or it's an all-in-one security appliance that'll combine firewall, virus scanning, spam, malware. It might include an intrusion detection system. So you can buy a device that functions doing all of these different roles as well. And it can also include your switch and so on and so forth. Last term for the day, DMZ, the demilitarized zone. You have an internal LAN. That LAN will have resources on it, file servers, email servers, print servers. None of those services should be visible to the rest of the world at all. However, there may be some devices on your network that you do want visible to parts of the world or even to most of the world. You might have a company web server where the files for your company, publicity, et cetera, are available. You don't want it out on the internet. I mean, maybe you're hosting it on the internet. You want it within your organization so that it is secured and maintained by your IT department, but you don't want it, you need it to be partially available. So a firewall can be a physical device, or again, it can be just a server with some software set up on it, but it should have 3 separate network segments. One connection, one interface will go out to the rest of the world. And that one, you're monitoring all the traffic coming in, you're monitoring all the traffic going out. Very limited stuff is allowed in. Then, one arm will go over to your DMZ. Your DMZ will contain your web server. It might contain some other types of servers that need to be accessed through the internet, but that do not contain sensitive company information. You're paying close attention to what traffic is allowed in and out there. If you don't have an FTP server, that's where you block ports 21 and 23. And then the stuff that gets almost nothing through is the stuff that goes into the LAN. You don't need anybody reaching into your LAN. Commonly, folks on your LAN will reach out for web pages. They will reach over for material that might be in the DMZ. So they walk you through the DMZ as part of Chapter 8. That's all I've got as far as information on the screen in front of me. Do you have questions about any of that specifically? It's a lot. Okay, so I'll warn you again, the videos for Chapter 7, if you find that when you're watching, I would highly recommend that, in addition to watching him type in show, run, configure router and this, that, and the other, all the command line stuff that he's doing, if you find that it's miserable, don't sweat it. Sit through it, toothpicks for the eyeballs if you need to, and then go out to YouTube and look for the fact that you can configure a router. Now you can connect to your router using standard Ethernet cables. You can connect to your router using a rollover cable. That's going to be a serial port on your machine to an RJ45 that goes into a specific port on the back of the router. You can also connect to the router. There are lots of ways to connect to a router. Fine. When you connect to the router, you can use a command line interface. That's what he does in the videos in Chapter 7. But most routers these days also have a graphical user interface, and it's much nicer to use, much harder to mess up using the graphical user interface. Go to YouTube and type in configure Cisco router using GUI, and you'll get videos that show you how to enable the right routing protocols that allow you to determine how much is shared and how much is not shared, that tell you, go in and type in configure firewall using graphical user interface, and you'll get some of the videos that maybe are a little less daunting than some of the stuff from the labs. Just a suggestion, all right? You must work through the labs to pass the class. A few folks are behind on the labs. It's not like when we get to the end of the term, you can take the exam, pass it with a great score, and I can give you credit for the class. My head of department can see all UMUC students how they've done on the labs. And he has the right, if not the obligation, to check that I am not passing anyone who didn't finish the labs. So you must finish the labs and the quizzes in the labs.
Sometimes those labs are a little frustrating because the long labs, right? Like they are like, there's like a lab in chapter 5. It's like 33 steps.
I know.
And I know I did every single step in there.
Yep.
And they told me I didn't do a step.
Yep.
And I'm like, are you kidding me?
Because you didn't click to check a particular like IP config or something. Or I went to IP config to check that my thing was okay, and they wanted me to click on the icon in the bottom right hand corner instead.
Yep.
And I used the command line because that's what I grew up with. So
But if
yeah.
you missed one step, do you fail that?
No, you don't fail the lab. All you've got to get a passing score of 90% on the lab. And when you get to your grade book, I don't know if you guys even get to see a grade book.
I don't get a chance to see a grade. Well,